Good morning, everyone. As Dave mentioned, one of the key ingredients of the EquiSim platform is the rupture model generation. So in this talk, which is kind of short to introduce everything, I will just talk a little bit about the source representation in these simulations that were used to develop this synthetic database, and also try to convince you about our confidence that we have in our simulation capability and the rupture model itself by showing examples of comparisons with real data, but also with empirical data. So when we build a rupture model, the objective is to have a kinematic rupture model that can represent the source complexities that can be injected into the Earth structure to produce ground motion that have deterministic characteristics and that are also representative of the physics on a broad frequency range. So far, we have been working more in the frequency range 0 to 5 hertz, and Dave mentioned that our capability is to model even high frequencies, but we have a limited knowledge actually right now on the velocity models that are used to go to those high frequencies, but also some other physics that need to be included in our simulations. So first of all, we need to have rupture models that are constrained by physics. They should be capable of reproducing near-fold ground motion characteristics, and not in terms of amplitude only, but also frequency content. And also, they should also be able to produce ground motion at long distances by convolving those with the wave propagation. There is also a requirement that we need to have rupture models that can be controlled by a limited number of parameters. Those parameters have to be very clear so that the users of the software can easily adapt those models to their needs. They need to, of course, validate it against ground motion, and that's what I will focus a little bit today, and also as Dave mentioned. We hope that for people who really would like to use the database, we hope that they will also look at the rupture models so that they can use those rupture models to do their own simulations using other techniques. So we are trying to be open, and the reason why we tried that is that we did learn through this experiment that lasted almost 5 years, that without this interaction between seismologists and engineers, you cannot do progress in both directions. So we are very grateful to this opportunity that we also try to improve our rupture models by working with the engineers. So I think for those who are not familiar with the rupture generator, we're trying to capture the source variability both in space and time using a technique that is based on dynamic rupture modeling to constrain the time history of the rupture movements, of the fault movements, and we also would like to have a good representation of the knowledge that we have gained based on past earthquakes. So not just rupture dynamics, but also trying to get some kind of empirical knowledge through the history of modeling earthquakes in terms of reproducing the kinematics. And so the rupture generator from the very beginning was designed on these two pillars. One is to correctly represent physics-based simulations using dynamic rupture modeling, but also try to correlate some of the parameters that are characterizing the kinematics using what it was observed in the past from kinematic rupture models that were inverted from the near-fold ground motion of large and small earthquakes. But we also, as I mentioned, we are still in the process of improving the model once we get new data, and we have been lucky that now there is a lot of new earthquake data. They're even closer to the fault, and this is a nice opportunity to improve our rupture model. One of them was by combining dynamic rupture modeling of large earthquakes, and we found out that the sleep rate function not only changes in terms of frequency content, but also its shape. And that was a requirement that was made also by our Japanese colleagues, that they noticed that even the rupture model was not able to produce ground motion at very long periods or the permanent displacement. So we have to make sure that a rupture model not only generate accurate velocity, PGV or PGA, or the frequency content of the observed signal, but also we want to have a rupture model that can predict very well the permanent displacement and the long period that are generated from the source and propagated. So we recently tried to improve that, and the current rupture model that we're using now for this platform include all these recent developments. So I'm going to go fast on this. As Dave mentioned, the idea is to have an initial database that will capture some of the major rupture characteristic for a scenario earthquake on the Hayward Fault. That means that with a limited number of organization, we want to make sure that whatever we give now to the engineers is a database that will have some kind of trusted rupture effects into the ground motion. So we have to fix some of the parameters for this database. We fix the magnitude, the fault depth, the geometry, the deep angle, and the subfault dimensions, which are related to the maximum frequency. But we also did vary some of the parameters, and one of them is the fault length, the fault width a little bit, the rupture initiation, which I will talk a little bit, and we try to have a set of synthetics that is balanced between rupture models that were produced with rupture models that are fully stochastic and rupture models that are kind of hybrid. So in the future, as we all realize, is that we need to have rupture models that will correctly reproduce the observed ground motion variability, and which is not very well represented in our ground motion models. So we will rely on a parameter space, which is going to be much broader than what it is right now, and that includes a list of parameters. But one of them I want to point out, and I think the seismologists will agree with me, is the rupture area. That is a parameter that we have been deriving from some empirical relationship, but we have not seen how sensitive, or fully seen how sensitive is ground motion based on the rupture area. And based on this experiment we have been doing, there have been so many unknown results or unexpected results just based on changing the rupture area. The other thing that we do here is that we use Martin Mice empirical observations about where to put the hypocenter location. Usually they found that magnitude 7 earthquake, they start rather deep, and that's why we put our hypocenter at 8 kilometers. But also they found that the initial, in terms of strike direction, there is no preference. So that's why we choose 5 locations to better represent the variability of the rupture directivity effect on our scenarios. And these are just some representation of the how the rupture looks like for a bilateral case or unilateral rupture. And like I said, we did also use now slip patches, and we have now 2 different techniques that can be available to everybody. The most recent one was developed by Rob Graves, that avoids a kind of square-like rupture patch in our code, in our program. And Dave talked a little bit about why we need to have this kind of selection of hypocenters. We need to know how much variability we get just by looking at the directivity effect, and our scheme does include very well not only wave propagation effect, but also the source effect that are very visible in this snapshot of the wave field. Now, I would like to move on validations of the technique. As we know, we cannot capture the ground motion variability with only one realization. But as I show here in this plot, this is a nice example showing that even one single realization with our scheme behaved very well in terms of comparisons with the ground motion prediction equations. For this case, this is a function of distance. And as you can see, the fit is relatively good. So that means that at least from a general point of view, the rupture is capable of producing ground motion at the level that was predicted or observed from past earthquakes. But if you put now the median realization, which is the median of 50 realizations, you can see that we still do very well in terms of fitting the ground motion models, even at long distances. But what I want to point out here in this figure is that the standard deviation that was predicted by ground motion prediction equation, it's almost 0.6, and it's almost flat for the PGV, and has some changes in PGA. Our simulation is still low, but this is because we're just using one single scenario or several realization of single scenario. I'm sure that if we move on to a much broader database, we kind of we will get closer to the 0.6. But what I want to make a point here is that actually the standard deviation that is predicted by the simulation is distance dependent and also is frequency dependent, which is not very well characterized in ground motion models. Now, it is important to actually validate our rupture models, not only using ground motion prediction equations, but also real data. And I have a poster showing here for those who are interested. We were very successful in actually, with a couple of single realizations, to capture the ground motion that are recorded in the Bay Area during the Loma Prieta earthquake, which was very well recorded. And here I show an example where if we really want to pin down the waveform characteristic at long periods, we really need to go and get a model that has those patches. Otherwise, you could easily kind of on average reproduce the characteristics of ground motion, but you'll miss some of the long period. And I can discuss with people that are interested how we did that for this earthquake. But this is kind of nice because it builds confidence that in the area we're trying to produce a synthetic database. We're also capable of fitting actual recorded data. But it's important to move on now to how this rupture generator has been performed in other parts of the world. And as you know, as Roberto mentioned, we do have two different techniques. One is hybrid and one is fully hybrid, which combine fully deterministic and stochastic or other ways. But we also have the fully deterministic approach that we have been using here. In this case, I only show cases where we use the deterministic approach all the way to 5 or 3 hertz. This is the earthquake Ridgecrest, this is Norcia, and the other one is Amatrice. As you can see, we do a very good job in fitting the recorded motion when we use this type of rupture generator that has some kind of deterministic representation of the slip. If you move on to the work that Rob Graves did based on the broadband platform developed by SCAC, where they use actually the hybrid scheme, which is deterministic 0 to 1 hertz, and then stochastic above that, you can see that for a wide range of magnitudes and distances and different geological structure, the rupture generator performed relatively well. So this is kind of building some kind of confidence that we are in a good direction in terms of having a rupture generator that has been kind of successful in the past to model past earthquakes. And if we now move to other areas, one of them is Japan and the other one is New Zealand. Brandon Bradley has done an extremely valuable work on developing ground motion modeling techniques that have been tested heavily on really good data. And the example they show here is that actually the simulation based on the GP rupture performs even better than the ground motion models, especially at some long periods. So this is some kind of an experience that we would like to continue and apply our prediction capability in other parts of the country, including Japan, Italy, and New Zealand. So the other, and I don't have enough time, but we are also working with Vladimir Grazer at NRC to actually use simulations to improve the ground motion models that are developed for central US. As you know, there's a gap in this part of the country because we don't have large earthquakes. We don't have really good data, near-fault data. And what we found is that their empirical models, they behave relatively well at short distances. That means that there is some kind of saturation with distance. But if you, simulations suggest that if you move to smaller magnitudes like 6.5 or 6, you can see that there is undersaturation that is not well predicted by some of the ground motion models produced for that part of the country. And what we also observe, which is very helpful for the engineers, is that it depends on this, the faulting, that the ground motion could be different. Like for a magnitude 7 earthquake, for strike slip faulting, you have a flat or a saturation of ground motion with the distance. But if you move on to a thrust fault, the ground motion not only is much higher near the fault, but also there is undersaturation, and that persists in almost all periods. So this is a very interesting result that Vladimir is using to actually improve the ground motion models for that part of the country. So this is a nice application of the current technique that we're using here in the Bay Area to other parts of the country to improve the ground motion models. And I think I'll stop here. This is a list of publications that were generated by this project. And there's lots of interesting discoveries based on just synthetic ground motion simulation, based on just this database. And the list is long. Maybe I have not included all of them. But there are some nice posters outside that I encourage you to see, because our talented postdocs and young scientists have produced a lot of results that are really very encouraging. And with that, I would like to thank you.